This program analysis and a bunch of differential privacy. We're going to start out with Wei Hao Chu giving a talk on relational cost analysis for imperative or functional imperative programs. Thanks.
Hello? Okay. Hello, everyone. Thanks for coming. My name is Wei Hao Chu, and today I want to show you a type and effect systems which will provide relational cost analysis for functional imperative programs. Let's start with cost analysis. The standard cost analysis aims to statically establish a lower bound or an upper bound on the evaluation cost of a single program. And this cost is usually measured in abstract units, which means the cost can be the number of the reduction steps in operation semantics. It can be even the number of the recursive call made by a program. And there are many techniques developed for the cost analysis. One of them I want to show is through type and effect systems. And in such a systems, this type is usually enriched with annotations to track the effect. So when it comes to the cost analysis, this effect will become the cost. And looking at the typing judgment of such a systems, a program T of type A under the context gammas will now have annotations to track the lower bound and upper bound of its own evaluation cost. And similarly, at the type level, an arrow type now has annotations to track its evaluation cost of its function body. And the benefit of having this type and effect system is that the cost informations can be obtained via typings without actually running these programs, and which is static analysis. And this is already a very well-studied topic, but today I will not focus on it. What we are really interested in is to provide cost analysis in the relational setting on two programs. And the aim of the relational cost analysis is to statically establish an upper bound on the difference in the cost of two programs. And this difference is called relative cost. Having such an upper bound on this relative cost can be very useful. For example, when it comes to the resource-aware compiler verification, a zero upper bound can be used to prove that the optimized code will always run at least as fast as the original code. And there are many methods we can use to get this upper bound. Standard method is the worst case, best case analysis, which will compute the best case and the worst case evaluation cost and then take a difference. However, in some cases, this is very naive and not precise. So we want to have a system that can provide a tight upper bound. And then we try to figure out some type and effect systems. And we find one, which is a refinement type and effect systems called real cost from POP 17 that can help us. And the key idea of this real cost is that rather than compare two programs separately, as we have seen in the worst case, best case analysis, it will now analyze two programs simultaneously to explore the structural similarity of two programs. And the typing judgment of real cost will now analyze two programs, T and T prime, simultaneously. And they will be related at the relational type, tau, with the relative cost of these two programs, upper bounded by this annotation D. And if we see the relational type here, it will now be interpreted as a set of pairs of values. In order to track the cost, we will add annotations to the arrow type. So now this arrow type can be interpreted as a pair of two functions whose execution cost difference is upper bounded by this D, as long as this argument will be related by the type tau1. So far, real cost works well, but it's limited to only the normal functional data structure. What we are interested in is to handle the mutable data structure. And the reason is that the mutable data structures will permit destructive updates, which are very widespread and sometimes will help to improve the efficiency. However, mutable states will become more difficult to reason about than those normal functional data structure. And in this work, we will only consider mutable arrays, which is simple examples of the mutable data structure. In particular, we designed a type and effect systems called AREAL, where this A will stand for arrays. And now, this AREAL can provide relational cost analysis for high-order functional imperative programs with mutable arrays. Going to the contribution of our AREAL, it consists of 4 parts. First, it provides type and effect systems, which can provide relational cost analysis, supports mutable arrays and the array-based operations, which will help us to improve the expressiveness of relational cost analysis. And we also have a lightweight refinement of those array-based computations. And these will be used to provide a more precise relative cost upper bound. And I will show this in the later examples. Then we also have a soundness proofs for our systems via logical relation models. This is our theoretical foundations. And finally, I will show an implementation of our AREAL, which is based on bidirectional type checking and shows the practical utility of our systems. In this talk, I will only focus on the first 2 contributions. Let's go into more details about our systems. The first challenge I have faced is how to treat a state. In order to express 2 arrays of the same length, we choose to add the type for the arrays. And now this type tau in the array type will be relational, and it will relate to corresponding element in these 2 arrays. And also, we choose to have an index to track the exact length of these 2 arrays. Since now we have the index, we also allow our type to quantify over this index. And the next thing is that our arrays now will have destructive update, and they will be a part of the heap. So in this case, at the expression levels, we'll have those array-based operations, such as read an arrays, update an arrays, or like a sequence of array operations. And in our systems, we will view these array-based operations as impure computations that will access the heap with side effect. And these array-based computations will be now internalized with our relational or triple star monadic type. And I will leave these monadic types later for more details. And let's first have a look at a simple example. This example is a functional imperative in-place map, which is just a standard map functions, but now works over the mutable arrays. I will build it from scratch. So suppose I will first define a map function, and f will be the mapping function. Then this input A will be the input array, k will be the starting index of this map function, and we'll track the length of the arrays. And in the function body now, it will first read the arrays at index k, and then update this element by applying this mapping function. So let's pay attention, because this read and update will now be considered as impure computations. And after the update, this map will now work over the next index to continue the mapping over the rest of the arrays. we have seen these map functions. I want to first show you a simple type of this map. The only thing I want to mention is that this function body now contains the impure computations, and it will be regarded as a Monarch type. And the return type of this map function will be unit. Then, actually, about these examples, what we are really interested in is to take two rounds of this map function. Specifically, when we have the same mapping function f, but different arrays, but still of the same length, we want to figure out what is the maximal variations in the cost of these two rounds. And this will bring us to our relational cost analysis. First of all, compare the two same functions where incur no relative cost. And here we have a box, which is a refinement, enforce a pair of identical values. So in this case, it will give us the same mapping functions. And then the relative cost of execution these two map functions on the two rounds will now appear as the annotations in the monadic type. To better understand these map functions, I want to start with two arrays. Right now, these two arrays will have the same length, but the content may differ. And since we have the same mapping function f, so we can figure out that the cost variations of these two rounds will now depend on the variation of these two arrays. In this case, we want to track the information about the variation of the two arrays. So we will start to compare the two arrays and then figure out the indices where these two arrays differ. And in the systems, we make our preconditions to record these indices where these two arrays differ. And now in the monadic type, the information about the variation of two arrays will be stored in the precondition and the postconditions. And one thing I want to say is that this precondition and the postconditions are relational, and because they will contain the information about the two arrays. Additionally, this return type is also relational, which will correspond to a pair of return values. Next, which will be a very important part of our system, is that we will consider this precondition and postconditions as a lightweight because they only contain the information where two arrays differ, and they do not contain other information about the content of the arrays and other things. And we will view these preconditions and postconditions as a refinement. And actually, even though our refinement is very lightweight, I will show that it can be still very useful to provide a precise relative cost upper bound. So let's go back to our in-place map examples. Now with our new monadic types, we can make the typing more interesting. First, since we have the same mapping functions because of the box refinement, the set of indices where these two arrays differ will now only reduce after the mapping. So which means it will be safe to have the same preconditions and the postconditions because this postcondition P here will be an upper bound on the set of indices where the two arrays differ. And another interesting point is that look at the relative cost upper bound D. It will now become a function over this precondition P, and which can be understood in the following way. Suppose this will be the two input arrays. And now we know that we have the same mapping function f on the two rounds. Then at indices where the two arrays are the same, which is the false indices, then which means that we are applying the same functions to the same array element, and it will not incur any relative cost. So in this case, we will find that the relative cost will only be generated at indices where the two arrays differ. And this is what we can rely on from this precondition. Now we can have our new relative cost upper bound by counting the number of elements in these preconditions at the working range of the math function, which is from k to n. And this R will be a relative cost upper bound by applying this function, mapping functions with the array elements. So far, we have seen the typing of our examples. Now let's look at the typing judgment for the impure computations. We have those typing judgment for all the array-based operations. I will show one, which is the update. Suppose T1 and T1 prime will be the arrays we want to update. And the index I primes will be the place we want to update these arrays. We will use T3 and the T3 prime to update. In this case, when we start from the precondition P, we have larger postconditions, because right now these I primes will appear in the postconditions, because this T3 and the T3 primes may differ after the update. And actually, these rules can be even more interesting. Remember, we have the box. So in this case, if we restrict this T3 and the T3 prime to be identical, which is the box, then which means the index I prime can never appear in the postconditions. In this case, we have a smaller postconditions. And also, in these rules, we will check the array bound limit. And so far, all these rules we have seen, it is proved sound via logical relations. And we have a new logical relations with the idea of the critical words, step index, and it will account for the new refinement of the state monad. And so far, this system we have seen, it is declarative. So we use bidirectional type checking to organize our systems. And the constraint will now contain the cost, array size, and the assertion piece. I will show a list of the imperative function imperative examples verified by our type checker. Some of them will take a longer time because of the complexity of the constraint that will contain some set operations. To conclude my talk, we first show AREA, which is a type and effect systems provide rational cost analysis for function imperative programs now with multiple arrays. We also have a light design for the refinement of the array-based computations, show you soundness proofs of our systems, and also implementations, which are type checkers, and also show the examples. Thanks again for coming, and I'm ready for the questions.
Great, thanks. We'll start with a question from Slido, and then if there are questions from the audience. So can you relate two different programs or only two runs of the same program?
We can do for the same program, but for different input, or the two different two programs.
So if the two runs have different control flow,
yes.
How do you handle that?
Two runs of different control flow.
Would two runs with different inputs produce different control flow, like an if statement or something?
Then we will go back to the best case, worst case analysis.
Okay. Audience?
In the map example, you assume that on array indices where the arrays have the same value, the cost will also be the same. But I think this is only true if your mapping function f is pure, but your language has impure elements. So I think it could depend on the history of what has been seen before. So I don't think this assumption is really valid in your language.
Could you repeat again?
I mean, you had this monadic type and you had this PQ, you had postconditions, and then you were saying, yeah, but they are actually the same as long as the element values are the same. So if your language were pure functional language, I would agree. But because your language is an impure language with side effects, I don't agree. Because you may still have different computational cost on the same input if the history of computations that has been done before differs.
We did not track the history of this. And I think in the definition of the precondition and postconditions, it says that gives you that the two elements may differ, but not means it must be different. But yeah, maybe I think it's a good question. If we can,
maybe we can just
I want to
take this
discuss offline, possible, yeah.
Just to comment to that, as I understood it, all of the expressions that have a function type, they are actually pure, because every impurity will show up in the type system, right? So it should be fine.
Great. Another question from Slido. Can you elaborate on the duration of type checking? Is it doing a proof, or is there SMT running? Can you explain?
Okay, so for the type checker, we will first generate the constraint and use the SMT solver, and then these SMT solvers will solve some constraint, say if it satisfies the array bound limit and some other things, then it will generate a final constraint, and we'll use that final constraint to check if this type is valid or not.
Okay. One more question from the audience? Yes, and if you want to get set up.
Hi. So I have questions about the PQ thing. So you said that was like a monad, right?
Could you say it's like what?
Like a monad.
Yeah.
Yeah. So, I would have thought the way I think of functional imperative, maybe I'm misunderstanding what you mean by it, but it seems like monadic effects exist in how you do effects in purely functional languages, not in functional imperative ones, right? So I guess I don't really understand what is the status of this PQ thing in your work.
This PQ, we actually use hot triple style monadic type, but these types were only for those array-based computations. And this P and the Q will now tracks the positions where these two arrays may differ. And I don't know if I answer your question.
We can take it offline. We should start the
Yeah.
next talk. Can you select the speaker again?